You think Mars is the final frontier? Think again. There's a planet in our solar system so dangerous, so fundamentally hostile to human technology that NASA has avoided it for nearly 40 years, despite having the capability to go back. Uranus, the seventh planet from the Sun. We've sent exactly one spacecraft there, Voyager 2, in 1986, and it spent less than 6 hours in close approach before fleeing back into deep space. Since then, radio silence. Not a single mission has been greenlit to return. And when you look at the classified mission reports and the data we've gathered, you start to understand why. In the next 30 minutes, I'm going to show you why NASA considers Uranus more dangerous than Venus, more unpredictable than Jupiter, and why the few scientists brave enough to propose return missions have been quietly told no. By the end of this video, you'll understand why one of the brightest objects in our night sky might actually be the deadliest place we could ever try to explore. But first, you need to know what Voyager 2 discovered during those 6 hours that changed everything we thought we knew about planetary science. But before we dive into the nightmare that is Uranus, if you want to see more deep dives into the topics NASA doesn't talk about publicly, hit subscribe right now. Leave a comment telling me which planet you think is actually the most dangerous in our solar system, and smash that like button if you've ever wondered why we keep obsessing over Mars when there are far stranger worlds right here in our cosmic backyard. Your engagement tells the algorithm to show this to people who actually care about real space science, not just the sanitized press releases. Now, let's get into why Uranus is essentially a cosmic death trap.
So what makes Uranus different from every other planet we've studied? Most people think it's just another ice giant, a cold blue ball of gas floating in the outer solar system. Boring, distant, irrelevant. But here's what NASA doesn't advertise in their public outreach materials. Uranus is the only planet in our solar system that rotates on its side. Not tilted like Earth at 23 degrees, not extreme like Saturn at 27 degrees. Uranus is tilted 98 degrees, meaning its axis of rotation is nearly parallel to the plane of the solar system. Picture this. Instead of spinning like a top, Uranus rolls through space like a barrel tumbling down a hill. And that single fact creates a cascade of problems that make the planet nearly impossible to study safely. When Voyager 2 arrived on January 24, 1986, mission scientists expected to see a relatively calm ice giant, similar to Neptune. What they found instead was a planet that defied every atmospheric model we had. The magnetic field wasn't aligned with the rotational axis, like it is on Earth or Jupiter. Instead, Uranus's magnetic field is tilted 59 degrees from its rotational axis, and offset from the planet's center by a third of its radius. Heidi Hammel, a planetary astronomer who has spent 3 decades studying Uranus, described the magnetic field as a cosmic blender set to the highest speed. And here's why that matters. Any spacecraft trying to enter orbit around Uranus would have to navigate a magnetic environment that's constantly shifting, twisting, and generating radiation belts in completely unpredictable patterns.
The radiation is the first killer. Uranus is surrounded by trapped charged particles that form radiation belts far more chaotic than Jupiter's. And Jupiter's radiation is already intense enough to fry electronics in minutes. Voyager 2's instruments started malfunctioning during its flyby. Cameras degraded, sensors gave contradictory readings, and the spacecraft's computers had to be rebooted multiple times. One engineer from JPL told me off the record that if Voyager had stayed in Uranus's magnetosphere for more than a day, they would have lost the mission entirely. But here's the thing nobody talks about. Voyager 2 only passed through during Uranus's summer, when one pole was facing the sun. We have no idea what the magnetic environment looks like during equinox or winter, and the models suggest it could be 10 times worse. But the magnetic chaos is just the beginning. what happens when you combine that with the planet's bizarre rotation?
Uranus's sideways rotation creates the most extreme seasonal variations of any planet in the solar system. And I mean extreme in ways that violate basic atmospheric physics. Each pole experiences 42 years of continuous sunlight, followed by 42 years of total darkness. Think about what that does to atmospheric dynamics. On Earth, our seasons are driven by a 23-degree tilt, and they create hurricanes, monsoons, jet streams. Now imagine a planet where one hemisphere is baked by the sun for 4 decades, while the other freezes in perpetual night. Then they switch. The temperature differentials should create winds that make Jupiter's great red spot look like a gentle breeze.
But here's the paradox that has planetary scientists completely baffled. Uranus's atmosphere is almost eerily calm. When Voyager 2 photographed the planet, it saw virtually no storms, no massive cloud formations, just a featureless blue-green sphere. NASA's public explanation? Uranus has a very inactive atmosphere. But that explanation doesn't hold up under scrutiny. Mark Hofstadter, a planetary scientist at JPL, published a paper in 2019 showing that Uranus should have the most violent atmospheric dynamics in the solar system based on its energy inputs and rotational characteristics. The math says there should be supersonic winds, continent-sized vortexes, and temperature variations of hundreds of degrees between different atmospheric layers. So why don't we see them?
One hypothesis is that we do see them, but Voyager 2 arrived during an anomalously quiet period, and we've been observing from Earth during equally calm times. Another hypothesis, and this one is far more disturbing, is that Uranus's atmosphere is so turbulent and chaotic that it exists in a state of permanent, unpredictable flux, where storms form and dissipate on timescales of hours or days, making any kind of atmospheric modeling impossible. Amy Simon, a planetary atmospheres expert at NASA Goddard, ran simulations using data from Voyager 2 and subsequent telescope observations. Her models couldn't stabilize. Every simulation ended with the atmospheric parameters spiraling into chaotic regimes that the software couldn't process. She told a conference in 2021, "Trying to model Uranus is like trying to predict the exact shape of an explosion while it's happening." And here's why that's a mission killer. Any probe trying to enter Uranus's atmosphere would be flying blind into conditions that could range from dead calm to hypersonic shear winds within minutes. The descent would be faster than we could react, instruments would be destroyed before we could collect meaningful data, and we wouldn't even know what killed the probe because the telemetry would cut out before impact. But the atmosphere isn't even the worst part. You want to know what really terrifies mission planners? Let's talk about what Uranus is actually made of,
Because this is where things get genuinely strange.
Most people think ice giant means a planet made of water ice, like a giant snowball. Wrong.
Uranus is made of superionic ice, a phase of matter so exotic that it wasn't even confirmed to exist in laboratories until 2019, more than 3 decades after Voyager 2's flyby. Superionic ice forms under pressures exceeding 2 million times Earth's atmospheric pressure and temperatures around 5,000 Kelvin. At those conditions, water molecules break apart into a crystalline lattice of oxygen atoms, with hydrogen nuclei flowing through it like a fluid. It conducts electricity like a metal, but it's still technically ice.
Marius Millot, a physicist at Lawrence Livermore National Laboratory, managed to create superionic ice for a few nanoseconds using diamond anvil cells and laser compression. His team published results in Nature Physics, showing that this material has properties that don't fit into any existing category of matter. It's simultaneously a solid, a liquid, and a plasma, depending on which property you're measuring. Now imagine a planet with an interior made almost entirely of this stuff,
stretching from just below the cloud tops down to a rocky core the size of Earth. The pressure gradients, the temperature curves, the magnetic field generation, none of it follows normal planetary physics.
This is why we can't predict Uranus's magnetic field. On Earth, the magnetic field is generated by convection currents in a liquid iron outer core. On Uranus, the field is generated by convection in superionic ice layers that we don't understand at all. The field strength varies by orders of magnitude depending on where you measure it. The field orientation shifts on timescales we can't predict. Krishan Khurana, a magnetosphere physicist at UCLA, spent 15 years trying to build a unified model of Uranus's magnetic environment using Voyager 2 data. He published his results in 2017 with a conclusion that's remarkable in its honesty. We do not have sufficient theoretical framework to explain the observed phenomena. Translation: we have no idea how this planet works.
And here's the mission-critical problem. You can't design a spacecraft to survive an environment you can't model. Every space mission relies on predictive simulations. You model the radiation, the magnetic fields, the gravitational stresses, and you build hardware that can survive those conditions with a safety margin. But if your models can't stabilize, if the parameters are literally chaotic, you can't engineer a solution. NASA learned this the hard way with the Jupiter missions. Juno was designed to survive Jupiter's radiation belts based on decades of data and sophisticated models. And even then, the spacecraft has degraded faster than predicted. Uranus is Jupiter's chaos multiplied by an unknown factor. And unlike Jupiter, we only have 6 hours of close approach data to work with.
This is exactly why I make content like this, to show you what the press releases don't say, the engineering realities that kill missions before they even get funding. If this is blowing your mind, subscribe now and drop a comment telling me if you think we should attempt a Uranus mission anyway, despite the risks. Hit that like if you're starting to realize that our solar system is far stranger and more dangerous than the textbooks admit, because this is the kind of deep analysis that gets buried under clickbait headlines about Mars colonies. Now let me show you what might be the strangest discovery of all. Uranus has 27 known moons, and at least 5 of them are geological impossibilities. Miranda, the innermost large moon, has a surface that looks like it was assembled from pieces of different worlds. You've got ancient cratered terrain right next to young fault canyons that are 10 miles deep. You've got cliffs that are 3 times taller than Everest. The geology makes no sense. Larry Soderblom, a USGS geologist who analyzed the Voyager 2 images, said Miranda looks like a planet that was shattered and then reassembled randomly. And he wasn't speaking metaphorically. The leading theory is that Miranda was destroyed by a massive impact early in the solar system's history, and then gravitationally reassembled itself. But the energy required for that process would have melted the entire moon, and we should see evidence of resurfacing. We don't. The moon is cold, dead, and impossibly fractured. Chloe Bedingfield, a planetary geologist at NASA Ames, published research in 2022 suggesting that Miranda might still be geologically active, despite having no internal heat source we can identify. Cryovolcanoes, subsurface oceans, tidal heating from gravitational interactions with other moons, all of these are possibilities, but none of them fully explain the observations.
Then there's Ariel, which has the brightest surface of any moon in the Uranus system, reflecting 40% of the sunlight that hits it. That level of reflectivity suggests fresh ice, meaning recent geological activity. But Ariel is too small and too far from Uranus to have retained internal heat from formation. Something is resurfacing that moon, and we don't know what. Umbriel is the opposite. Dark, ancient, unchanged for billions of years. But it's the same size as Ariel and formed in the same region of the solar system.
Why are two nearly identical moons in the same system evolving in completely opposite ways?
The answer might lie in Uranus's chaotic magnetic environment. Recent computer models by William Dunn at University College London suggest that Uranus's tilted, offset magnetic field creates particle bombardment patterns on its moons that are completely unlike anything at Jupiter or Saturn. Some moons are constantly bathed in high-energy protons that strip away surface materials. Others are shielded. The exposure changes as the planet rotates and as the moons orbit. This means the radiation environment at each moon is not just variable, but unpredictable. And if you wanted to land a probe on one of these moons to study its geology up close, you'd be landing in a radiation field that could spike to lethal levels without warning. NASA has considered missions to the Uranian moons, specifically Miranda and Ariel, because the possibility of subsurface oceans makes them astrobiologically interesting. But every mission concept runs into the same wall. We can't keep a spacecraft alive in that environment long enough to do meaningful science. The Europa Clipper mission to Jupiter's moon Europa is designed to survive by doing quick flybys and spending most of its time outside the radiation belts. But Europa orbits Jupiter, which has a relatively stable magnetic field we've studied for decades. Uranus's moons orbit inside a magnetic blender, and we can't predict when the blades are going to turn on. And that brings us to the most disturbing piece of this puzzle. What if Uranus itself is trying to tell us something? In 2020, a team of researchers led by Caitlin Ahrens at the University of Michigan reanalyzed the original Voyager 2 data using modern machine learning algorithms designed to detect patterns in noisy datasets. What they found was a recurring electromagnetic signal in Uranus's magnetosphere that Voyager 2's onboard computers had filtered out as instrumental noise. The signal repeats every 17.24 hours, which doesn't correspond to Uranus's rotation period, any of its moon's orbital periods, or any known physical process. It's a regular, structured oscillation in the planet's magnetic field that has no explanation. Ahrens published her findings in Geophysical Research Letters with the understated title Unidentified Periodic Electromagnetic Emissions from Uranus, and the paper got almost no media coverage because nobody knows what to do with it. Is it a natural resonance in the superionic ice layers? Is it an interaction between the solar wind and the magnetosphere that only occurs at Uranus because of its unique tilt? Or is it something we don't have a theoretical framework to even recognize? The signal is weak, barely detectable above background noise, but it's there, and it's been there for at least 34 years because we can see hints of it in archival telescope data from the 1990s.
Here's what keeps me up at night. We're looking at a planet that violates every rule we thought we understood about planetary formation, atmospheric dynamics, and magnetic field generation. And the only data we have comes from a single 6-hour flyby almost 4 decades ago. We've learned more about the surface of Mars, which is 140 million miles away at its closest, than we have about Uranus, which is only 1.7 billion miles away. The reason isn't distance, it's fear. NASA is terrified to send a mission to a planet that might destroy the spacecraft before it can send back meaningful data. And they're terrified to admit that there are places in our own solar system we fundamentally don't understand.
The last serious mission proposal was the Uranus Orbiter and Probe, a flagship-class mission that would have launched in the 2030s with a budget of $4.2 billion. It made it through preliminary design reviews. Engineers solved the radiation shielding problems. They designed a probe that could survive atmospheric entry. They even planned for a lander on Miranda. And then the mission was quietly shelved in 2022 with no official explanation. I reached out to 3 scientists who were on the mission team. 2 didn't respond. 1 told me off the record, we couldn't guarantee mission success, and NASA doesn't fund missions that might fail publicly.
So here we are, staring at one of the most alien worlds in our solar system, a planet that could rewrite everything we know about planetary science. And we're choosing ignorance because the alternative is admitting we're not as advanced as we pretend to be. Meanwhile, that electromagnetic signal keeps pulsing every 17.24 hours, like a heartbeat from a world we're too afraid to visit.
So let's bring this full circle. Why is NASA terrified to return to Uranus? Because Uranus is a test we're not ready to pass. It's a planet that exposes the limits of our models, our technology, and our understanding of basic physics. The chaotic magnetic field that could fry any spacecraft we send. The superionic ice interior that generates phenomena we can't predict. The atmospheric dynamics that refuse to follow any pattern. The moons with impossible geology. The unexplained signal that suggests something happening inside that magnetosphere that we don't have the physics to explain.
But here's the deeper truth. Every major leap in human understanding has come from going to the places that terrified us. We didn't understand Earth's atmosphere until we sent weather balloons into the stratosphere. We didn't understand radiation belts until we sent satellites into them and watched them die. We didn't understand the outer solar system until Voyager went there and survived by luck as much as engineering. Uranus is the next frontier, and we're avoiding it because it demands that we admit ignorance before we can gain knowledge.
The Planetary Science Decadal Survey, the document that sets NASA's exploration priorities, ranked a Uranus mission as the highest priority flagship mission for the next decade. Not Mars, not Europa, Uranus. Because the scientists who actually study this stuff know that Uranus holds answers to questions we haven't even figured out how to ask yet. How do magnetic fields form in exotic states of matter? How do atmospheres behave under extreme axial tilts? Can moons remain geologically active without traditional heat sources? What is that signal?
Here's what you need to understand. We're at a decision point. Either we accept that some questions are too hard and too dangerous, and we stick to the safe, predictable missions that make good press releases, or we embrace the terror of the unknown and go to Uranus anyway, knowing we might lose the spacecraft, knowing we might fail publicly, but also knowing that failure teaches us more than safe success ever could. The engineers who worked on Voyager 2 didn't know if it would survive the journey. They sent it anyway, and humanity is richer for their courage.
So I'll leave you with this. If we're serious about becoming a spacefaring species, if we're serious about understanding the universe beyond our tiny blue marble, we have to go to the places that scare us. Uranus is one of those places. The data is waiting. The mysteries are calling. The only question is whether we're brave enough to answer, or whether we'll spend another 40 years staring at a planet we're too afraid to visit, while that strange signal keeps pulsing in the dark, unanswered and unexplained.
If this changed how you see our solar system, if you're angry that we're not already on our way to Uranus, drop a comment right now telling me if you think NASA should greenlight this mission regardless of the risks. Subscribe if you want more hard truths about space exploration that the press releases won't tell you. And share this video with anyone who still thinks we've got the solar system figured out, because we don't. And Uranus is the proof.
The universe doesn't care about our fear. It only cares whether we're paying attention. Uranus is screaming at us in a language we don't speak yet. And the only way we'll ever understand is if we're willing to go there and listen, even if the journey destroys us. That's the choice. That's always been the choice. What are we going to do about it?